Welcome to the Introduction to Battery Technology course. This lecture focuses on Chapter 5, which discusses nickel-metal hydride, NiMH, batteries. Learning objectives. In this chapter, we'll learn about nickel-metal hydride, NiMH batteries, how they work, their key components, and where they're used. As shown in the first image, NiMH batteries operate at 1.2 volts and 2,500 milliampere hour, compared to 3.7 volts and 2,200 milliamp hours for Li-ion batteries. This means NiMH cells have lower voltage but excellent stability and safety. The second image shows the basic structure: nickel oxyhydroxide as the cathode and a metal hydride alloy as the anode. During discharge, hydrogen moves through the electrolyte and generates an electric current. By the end of this lesson, you'll understand how NiMH batteries function and how they compare to Li-ion cells in performance and application. Terminology. In this slide, we're looking at 6 key terms that will appear throughout our discussions: electrons, overcharge, capacity, self-discharge, specific energy, and heat generation. These are fundamental concepts in battery technology, and understanding them will help you follow the later sections more easily. We won't go into detailed explanations here, but I encourage you to review the textbook and other reliable sources if you want to explore these terms further. As we continue through this training, you'll encounter many more technical terms like these, so consider this a starting point for building your battery vocabulary. Specific energy, also called gravimetric energy density, tells us how much energy a battery can store relative to its weight. It's measured in watt-hours per kilogram. It's an important performance indicator, especially for lightweight applications like electric vehicles or portable electronics. On the graph, we can see how 4 major battery types compare. Lead-acid has the lowest specific and volumetric energy density. NiCd improves slightly. NiMH performs better with higher energy per weight, and Li-ion stands out with the highest values, meaning it's both lighter and more compact for the same amount of stored energy. This comparison helps explain why Li-ion dominates modern applications, while NiMH remains a solid choice for cost-sensitive or durable designs. NiMH battery, advantages and disadvantages. This table compares nickel-metal hydride batteries with nickel-cadmium batteries. NiMH batteries offer clear improvements: higher specific energy, less memory effect, and good performance even at high discharge rates or temperature variations. They're also more environmentally friendly and easier to handle. However, they have some trade-offs: lower power output, shorter cycle life compared to NiCd, and higher sensitivity to overcharging and heat generation. In short, NiMH strikes a balance between performance and safety, but requires careful charging control to maintain reliability. NiMH, nickel-metal hydride, battery composition. This slide shows the basic structure and reactions inside a nickel-metal hydride battery. In the fully charged state, the cathode is made of nickel oxyhydroxide, NiOH, the same active material used in NiCd batteries, while the anode is a metal hydride, MH, material that stores hydrogen. The electrolyte consists mainly of hydroxide ions, OH, in water, which allows ionic movement between the electrodes. During discharge, the hydride at the anode releases hydrogen and electrons, forming water and hydroxide ions, while at the cathode, NiOH is reduced to NiOH2. This process releases electrical energy to the external circuit. When the battery is fully discharged, both electrodes convert to their lower energy forms. The anode becomes metal, and the cathode becomes NiOH2, while the electrolyte remains largely unchanged. This chemical balance between hydrogen storage and nickel reduction gives NiMH batteries their higher energy density and improved safety compared to NiCd cells. Negative electrode, anode, materials. Metal hydride. This slide summarizes the main types of metal hydride alloys used in NiMH battery anodes. The AB5 alloy, containing rare earth and transition metals like La, Ni, and Co., is the most common because it's easy to process and cost-effective, but it has lower energy density. The AB2 alloy, using elements such as T, Zr, and V, provides higher specific energy, but suffers from higher self-discharge, making it less practical for most applications. The A2B7 alloy offers the best performance, the highest energy density, and low self-discharge, but is more complex and expensive to produce. The table shows that AB2 and A2B7 types deliver nearly double the gravimetric energy of AB5, meaning they can store more energy per kilogram. Discharge. One half this slide explains what happens inside a nickel-metal hydride battery during discharge. As the battery powers a device, hydrogen stored in the metal alloy anode is released and reacts with hydroxide ions from the electrolyte to produce water and electrons. Those electrons travel through the external circuit to the cathode, providing electrical energy. Meanwhile, at the cathode, nickel oxyhydroxide, NiOH, is reduced to nickel hydroxide, NiOH2, completing the electrochemical reaction. This process maintains a stable output voltage around 1.2 volts until the battery nears depletion, when the voltage drops quickly to about 1 volt. There's a diagram on the slide to illustrate this reaction process, which we'll look at in more detail on the next slide. Discharge. 2/2 this diagram clearly illustrates how a NiMH battery delivers power during discharge. At the negative electrode, the metal hydride, NiMH, releases hydrogen, reacting with hydroxide ions, OH, from the electrolyte to form water, H2O, and free electrons, E. These electrons flow through the external circuit and the load, providing electrical energy to the device. At the positive electrode, nickel oxyhydroxide, NiOH, accepts those electrons and reacts with water to form nickel hydroxide, NiOH2, while regenerating hydroxide ions, which return through the alkaline electrolyte toward the anode. This exchange, electrons moving through the load externally and ions circulating internally, keeps the circuit balanced and allows the battery to continuously supply power until discharge is complete. Nickel-Metal Hydride, an overview. Let's take a quick pause here and look at this summary from Nickel-Metal Hydride, an overview on Science Direct. It nicely captures the key trade-offs of NiMH batteries. They offer higher specific energy, fewer toxic materials, less memory effect, and good deep discharge performance, all with strong environmental benefits. However, they also come with some limitations, such as higher cost, greater self-discharge, and lower efficiency compared to lead-acid or NCD batteries. Charge. 1/3 this slide explains the charging process of an NiMH battery. During charging, electrons flow from the cathode to the anode through the external power supply. At the positive electrode, cathode, nickel hydroxide, NiOH2, reacts with hydroxide ions to form nickel oxyhydroxide, NiOH, water, and releases electrons. At the negative electrode, anode, the metal alloy, M, reacts with water and incoming electrons to form metal hydride, NiMH, and hydroxide ions. This process stores electrical energy as chemical energy in the form of hydrogen within the metal hydride. We'll see the detailed electrochemical reactions and flow in the diagram shown here. Charge. 2/3 NiMH batteries are charged using a constant current method, but the process is more complex than that for NCD cells. A smart charger is essential. It monitors voltage, temperature, and time to detect the small negative delta V minus delta V, which indicates a full charge. Charge rates are typically 0.1 to 0.2 C, and temperature plays a key role. Charging is not recommended below 10 degrees Celsius for fast charge or below 0 degrees Celsius for slow charge, while high temperatures reduce charge acceptance. To prevent overcharging and extend battery life, chargers use multiple control methods such as time charge, voltage plateau detection, and temperature cutoff or rate of rise detection. Charge. 3/3 this graph shows how the voltage of an NiMH battery changes with charge capacity under different temperature conditions. As we can see, voltage gradually increases as the battery charges, remaining fairly steady until near full capacity, where a small peak and drop appear, indicating full charge, minus delta V detection. Temperature has a strong influence. At lower temperatures, 0 degrees Celsius, voltage rises more sharply and reaches a slightly higher peak before dropping. At higher temperatures, 40 degrees Celsius, the voltage remains lower overall, and the voltage drop at full charge becomes less pronounced, making charge detection more difficult. In practice, this means temperature control is crucial for accurate charge termination and maintaining NiMH battery performance. Overcharging NiMH batteries. Overcharging is one of the biggest risks for NiMH batteries. When the battery is fully charged but current continues to flow, heat builds up and causes internal damage, which reduces both capacity and lifespan. Just like in CD batteries, hydrogen and oxygen gases are generated near the end of charging or during overcharging. This can lead to pressure buildup if not controlled. To prevent this, smart chargers use safety timers and sensors that monitor voltage and temperature, automatically stopping or switching to trickle charge once full. That's why using the right charger is essential for safe and long-lasting operation. This concludes Chapter 5 of the Introduction to Battery Technology course. For deeper insights, please refer to the references provided on this page and consult the textbook to further solidify your understanding of the concepts introduced in this chapter. Once you feel confident with the material, you are encouraged to explore the additional resources available in this module, including lecture presentation, recommended YouTube videos, and supplementary readings. These will help you reinforce your knowledge before moving on to the practice exercises and, ultimately, the end of module assessment. Thank you. We'll meet again in the next lecture. Thank you. We'll meet again in the next lecture.